All right, well, all right, got it. Maybe we have to move the cursor over and they got it.
Yeah.
Probably weird if you leave the meeting right now. All right, well, thank you everybody for coming online and here in person. I'm excited to introduce Willem Collier from the University of Utah, who will be speaking today on confronting common data issues when evaluating a surrogate endpoint. And I'm going to turn it over to you and your first in-person speaking in since the pandemic began. I don't know if we're post-pandemic yet, but all yours.
Thank you so much, Dr. Alonso, and thank you for getting the keys here. Thanks everyone for meeting with me today and giving me this opportunity to speak with you. I know how renowned your group is, so it means a lot to have this opportunity. I'm going to talk about methods for the evaluation of surrogate endpoints, and this is work that I've been working on related to my dissertation, also at the University of Utah. And so just a little bit about myself personally before I get into work. I'm originally from the East Coast. My family's all from Massachusetts, but I grew up in Salt Lake City, Utah. My parents brought us out west so that we could grow up skiing and doing things in the mountains when I was very young. So I spent my childhood skiing. I wanted to be a professional skier until I discovered my academic interests, but I did a little too much of it. I don't actually ski. I haven't skied in 3 years. So most of the time I do activities that are more warm weather oriented, like mountain biking with my wife, Sarah, who's pictured here. She also grew up in Salt Lake. We've had
So they want to turn this. It's good to see you.
They don't want to see me.
There's too many gadgets.
No, we decided against Utah.
Yeah, I can vote on that. That's good to know.
Go right in.
Okay.
Check.
I just
George, I can't see his face, so put it up. Can you put it up a little bit? Right there?
Oh, yeah.
Okay, that's perfect.
Good.
Don't squat. Don't squat.
I was kidding. No, you're good.
That's good. That's good.
You should actually see it. We should be able to see it once you're talking.
Well, it's enough of these pictures. The main point is that I have this great dog here in the corner. Come with us wherever we go. So yeah, as I mentioned, I'm going to introduce my dissertation work. My dissertation committee is led by Drs. Tom Green and Ben Holland. And I work with these two and others in the Chronic Kidney Disease Epidemiology Collaboration, or CKD Epi for short. And
This should pick you.
okay.
Or we can put the mic. Or we can put the mic on you.
It's okay. Figuring it out as we go. So yeah, I work with this group, CKD Epi. It's really an international research group. It has two sort of core areas of emphasis, one of which is to developing equations to estimate the glomerular filtration rate, which I'll talk about in a moment, is a very important kidney marker of kidney function. And then the other area is evaluating surrogate endpoints for use in CKD trials for some complicated reasons that I'll talk about shortly. And so this group has been really exciting to work with as a graduate student. We collaborate and really are funded by the National Kidney Foundation, and then work in close collaboration with regulatory agencies, with FDA and also the European Medicines Agency. And so my thesis revolves around statistical methods for the evaluation of these CKD relevant surrogate endpoints, which really involves Bayesian hierarchical meta-regression methods. And then some related areas of emphasis include missing data methods and clinical trial design. And I'll talk about, for example, a missing data problem for the first part of the talk. But then also importantly, I come from a very collaborative interdisciplinary PhD program. And so I've worked with a lot of medical and surgical divisions at Utah, mostly on observational research before the surrogate endpoint work. So for this talk, I'm going to start with sort of an introduction to surrogate endpoints, how they might be used in clinical trials, with an example of a particularly interesting example of a surrogate for CKD trials. And then I'll talk about how a surrogate endpoint can actually be evaluated and what I'll refer to as a trial level approach. And then I have two projects that I can talk through, and depending on timing, I hope to at least get through project one, which is a missing data problem for surrogate endpoint evaluation. and then a second project again if we have time. So to define surrogate endpoints, consider that perhaps for a randomized controlled trial, we might be roughly interested in whether a new therapy causes a clinically meaningful benefit over a reasonable alternative for those with a specific disease. And of course, often we're interested in evaluating clinical benefit with an analysis that captures or estimates the treatment effect on an established clinical endpoint. So maybe the goal would be to evaluate whether a new therapy extends time to death relative to this reasonable alternative. But of course, RCTs can be limited when clinically meaningful events are rare, or especially relevant for the CKD setting if they occur long after the disease course begins. And so a validated surrogate endpoint can improve the potential for use of RCTs for evidence-based medicine in such disease areas. So what a surrogate endpoint is typically a measure of disease progression, such as often a biomarker, which is captured earlier in the disease course than the actual clinical event, allowing, for example, an analysis to capture a treatment effect on the surrogate endpoint with a trial perhaps with much shorter duration of follow-up than would be required for a time to event analysis. And then really crucially though, it should be that that treatment effect on the surrogate can be used to accurately predict the treatment effect on the clinical endpoint. And this really corresponds to, if you read, the FDA's documentation on surrogate endpoints, this is their expectation, at least in writing. So for CKD, the established clinical endpoint is time to kidney failure, often combined as a composite endpoint with mortality. And then I have KFRT to represent, RT represents replacement therapy, because once you've reached kidney failure, dialysis or kidney transplant is required. And those are, of course, intense interventions. And so you'd like to keep a person in earlier stages of CKD not requiring surgery, for example. But for many causes of CKD, progression from early stage CKD to KFRT can take possibly decades. And so, but importantly, it can be very beneficial to intervene on CKD early in the disease course to preserve adequate kidney function for longer. And this is especially because for very early stages of CKD, someone might have pathological kidney damage, but they might not have necessarily symptoms associated with that damage. And so it'd be ideal to identify therapies that keep them in that stage of the disease for longer. And so the slope of the glomerular filtration rate, or GFR, is a natural candidate surrogate endpoint for CKD trials. GFR is a measure of kidney function. It declines over time and defines CKD staging. So in short, a high GFR indicates a healthy kidney. And then once GFR crosses past a certain threshold, that indicates kidney failure. And then there are other stages of the disease in between. But the idea is that if a new therapy, of course, then slows decline in GFR for the remainder of a patient's life, then you would also ideally extend time to KFRT. And so I have a brief conceptual example to help highlight how we are thinking GFR can be used in a trial, and then also some of the potential drawbacks. So for here, imagine we have a conceptual trial in the counterfactual world for an individual patient, in the sense that we can apply a therapy, a control therapy, so represented through the red line to this patient, as well as an active intervention of interest, and then observe their GFR trajectory under both active intervention and control. And so say the person's GFR starting point is 80, which would indicate that there is kidney damage, but nonetheless, it's a fairly high starting GFR. Then maybe it would take about 8 years until, under the control therapy, the patient crosses the threshold for kidney failure. So the idea is that if you did a time to event analysis just for this individual patient's trial, it would have taken 8 years of follow-up to see that they benefited under the active intervention relative to the control. But there's a lot of information in this GFR trajectory that you missed out on if you just did this time to event analysis. And so specifically, the treatment effect on the surrogate endpoint is a contrast of the slope in the control arm, a long-term slope relative to the slope in the active intervention arm. And so ideally, if there's a if there's a difference in these two slopes, then that would indicate that the patient, well, in the appropriate direction, is benefiting under the active intervention. The problem, though, is that even if you did this slope-based analysis and you could capture a treatment effect on the surrogate, a difference in slopes at a much earlier time point, like 4 years, for example, if you actually stopped the trial there, this sort of requires an exercise and extrapolation in the sense that if you didn't have this long-term follow-up, you'd be assuming that this, even though there's this sort of long-term chronic improvement up to 4 years, that you would be expecting that that slope would remain the same for the longer period, so that the effect on the time to event endpoint would be what you would expect. And so this sort of helps highlight, I think, what the analysis of evaluation of surrogate endpoints emphasizes, is looking at whether or not the treatment effect on a surrogate corresponds to the treatment effect on the time to event endpoint of an appropriate size and direction. And so the CKD Epi group, as I mentioned before, has devoted a considerable amount of effort to address this question for CKD trials. And the way that we're doing this is through this Triallevel approach. And so here I have a scatter plot to represent one such analysis. So in this plot, the individual circles actually represent clinical trials, specifically a pair of the estimated treatment effect on the clinical endpoint on the y-axis, and then the estimated treatment effect on the surrogate endpoint on the x-axis for each trial. In this case, the size of the circle corresponds to the size of the trial. So bigger circle, a bigger trial. And so if you look at this association, you capture the fact, you can evaluate whether indeed, so in this case, an increasingly positive effect for this mean difference, treatment effect on slope, corresponds to an increasingly beneficial effect on the surrogate endpoint. And so if there's an increasingly beneficial effect on the surrogate, what we would like to see is an increasingly beneficial effect on the clinical endpoint, so a value for a hazard ratio further below 1 in this case. And so, of course, it's not just an evaluation of, a visual representation of a scatter plot. We actually fit a meta-regression model to capture the strength of the association across a collection of trials between the treatment effects on both of the endpoints to evaluate the quality of the surrogate. And so there is inference that helps define the quality of the surrogate through fitting a meta-regression model. And then just one more key feature here is that by fitting this model, it kind of provides a roadmap so that for any given treatment effect on the surrogate endpoint, you can develop a model-based prediction for a treatment effect on the clinical endpoint. And in particular, you can figure out how accurately, given for a particular set of trials, you can use a surrogate effect to predict a clinical effect. And so fitting this model sort of gives you the machinery to do the analysis that is expected by regulatory agencies. And so I'll just briefly mention that this trial-level approach has grown increasingly favored over what many refer to as an individual level approach. And so historically, there are sort of a few analyses that went into the evaluation of a surrogate in what's called the individual level approach. A part of this analysis, which is still important, is to look at the correlation between the endpoints themselves among individuals. But then a key part of the individual approach was evaluating Prentice criteria, which is really a mediation analysis, capturing the extent to which the surrogate mediates the effect of treatment on a clinical outcome. And this is sort of fell under criticism, quite well documented for a variety of reasons. I think one important reason is that this mediation analysis really requires strong and unverifiable causal assumptions. And then again, it doesn't really get at whether or not, so even if a surrogate mediates the effect of a treatment on a clinical outcome among patients in one trial, doesn't really allow you to capture whether a surrogate effect can be used to predict a clinical effect. So just to briefly highlight a meta-regression modeling approach, one that CKD Epi has historically used. I have a little notation here. And so for this meta-regression analysis, there's usually what this group has done is a 2-stage analysis, where in the second stage, a 2-level hierarchical model is fit. And so sort of key features here are that within each trial, you independently, as an independent between trials, estimate the treatment effects on the clinical and surrogate endpoints. And then other data input that's necessary are the standard errors of the estimated treatment effects for each trial. So I have these as the SCs of the theta hats, as well as a within study correlation between the sampling errors of the treatment effect estimates. And then these all serve as data input in the second stage model, the 2-level hierarchical model. And so again, a couple of key features here is that we typically have that through sort of central limit theorem, the treatment effect estimates are Gaussian. So we assume a bivariate normal distribution. And what's embedded within this first stage model is that the model takes into account that there's estimation error in the treatment effect estimates. And then these are really conditional on the thetas without the hat. These are the true treatment effects on the clinical and surrogate endpoint. And so many authors, the CKD Epi group has historically assumed a bivariate normal distribution for the true treatment effects, which induces this linear relationship between the true treatment effect on the clinical and surrogate endpoint. And so this conditional distribution that we get out of the bivariate normality assumption defines the meta-regression parameters, alpha, beta, and sigma e, that depending on the analysis, determine the interpretation of the quality of the surrogate. And then our group, we utilize Bayesian methods for model fitting. So I use RStan. So we utilize MCMC algorithms to generate posterior distributions. So that'll go into my first project, handling missing within study correlations and the evaluation of the surrogate endpoint. So as I just mentioned, there's sort of three levels or three data inputs necessary. I've broken these up: the estimated treatment effects on the clinical and surrogate endpoint for each trial, the standard errors, and then crucially this within study correlation as a third term. And so the effect estimates and standard errors are depending on the surrogate being evaluated, commonly reported in publication. But these within study correlations are rarely reported, require individual patient data to compute, and are commonly at least partially missing for the analysis. And so just a little bit more on that. Especially, so in the CKD setting, partial missingness happens because the CKD Epi group has worked very hard to collect individual patient data for a large collection of the trials. But as time goes on, more and more therapies are evaluated. And then also the trials themselves have evaluated patients with increasingly earlier stages of CKD because of the use of surrogate endpoints. And so the goal is to utilize more trials to continue to sort of substantiate surrogate validity. But our group is finding that it's actually getting harder and harder to get individual patient data. And so what would be ideal would be to do an analysis where you have within study correlations through IPD for some proportion of the studies, and you can do an analysis with the new trials without necessarily having to get this term for all of them. But then there are a lot of settings, it's important to emphasize, where a lot of analyses evaluating surrogates are happening where there's no IPD for any of the studies. It's a completely missing data input for these evaluations. So cancer is an example because a lot of trials are reporting estimated effects on what some refer to as surrogate endpoints like tumor response, disease-free survival, progression-free survival, as well as overall survival. And so many are doing analyses that just utilize the treatment effect estimates and the standard errors, and then either handle the complete missingness in some way or just assume independent sampling errors in the analysis. And so this is definitely discussed in the literature, handling this trial-level approach to surrogate endpoint evaluation. When the terms are completely missing, it's common for authors to assume these correlations are zero, impute a constant for all of the missing within study correlations. That's often motivated by subject expertise. Maybe there are bounds on the correlation that authors feel are realistic. Or sometimes there's some papers have demonstrated that there's a tie between the correlations of the sampling errors of the treatment effect estimates and correlations between the outcomes. And so they'll use observational data, transform a correlation between outcomes into one for the treatment effect estimates, and then use that Or in a Bayesian analysis, you can just assign a prior independently to each missing within study correlation. And some feel that, because this is a term that's between -1 and 1, then a uniform -1, 1 prior is appropriate. Alternatively, if they're partially missing, then you can utilize the available within study correlations to inform the non-missing terms for the missing terms. So a mean imputation, or some authors construct an informative prior using the available data and then assign that independently to the missing correlations. But what I just want to emphasize, which I hope this quote indicates, is that there's sort of the prevailing mentality is that these missing terms have sort of little capacity to influence the inference for the actual meta-regression parameters. So it's like this missing data problem can't influence the parameters that actually really determine the quality of the surrogate endpoint. But I guess we're finding that might not always be the case. And so what in this project I'm showing is that in certain realistic situations, handling of missing within study correlations can actually strongly influence the interpretation of the quality of the surrogate. And specifically, underestimating within study correlations can bias the meta-regression parameters in such a way that the analysis suggests a higher quality surrogate than is true in reality. And so then, as a result of simulation study and some in our real data analyses, we provide recommendations for how to handle missing within study correlations depending on data scenarios. And so I'll just go through a quick conceptual argument as to why this sort of problem arises. So in the two-level hierarchical model I demonstrated before, there are two sources of variability for the estimated treatment effects that we actually observe, and then also two sources of covariance. And so in this case, I'm sort of simulating a trial level scatter plot. And I did this so that I could first take draws from the between study model to obtain trial specific true treatment effects on the clinical and surrogate endpoint. And I'm representing those in the black with the black squares. And then the model, what it assumes is that for each pair of true treatment effects, there's a corresponding estimated treatment effect that's tied to the true treatment effect and essentially represents a draw from a normal distribution with additional noise due to sampling error. And so I fit, just in this case, just for sake of demonstration, just a simple linear regression line through the black squares. And so this line here is what we actually are sort of wanting to get at in the evaluation of a surrogate. It's the regression of the true treatment effects. But in reality, because only in simulated data do we have the true treatment effects, we don't know this regression line, but it is what we want to obtain. The parameters that define the line are what we want to obtain from the analysis. And so this red line instead represents a simple linear regression fit through the estimated treatment effects. And in this case, I've simulated, and this is quite common, in addition, a draw from a normal distribution from each pair of true treatment effects with a positive covariance or correlation between the sampling errors, so that there's a sort of a stronger relationship between the estimated treatment effects. So if you mishandle, the idea is that if you mishandle the within study correlations, if you underestimate them, then for example, the slope that you would obtain would be more likely to be that through the red line than through the black line. So I won't show details here, but just to emphasize that as a part of a paper that we're writing, we can show mathematically that that indeed the within study correlations cause bias in key terms like the meta-regression slope. So what we can show is, for example, for a collection of similarly sized trials, the location of the posterior mode for the meta-regression intercept depends on specification of the within study correlations. And specifically, the influence of the missing within study correlations depends strongly on the size of the standard errors of the trials. And in such a way that for larger standard errors, however much the within study correlations are underestimated, the mode in the meta-regression slope will be overestimated by approximately equal amount. Whereas if the standard errors are very small, so if you have a collection of very large trials, then handling missing within study correlations has little influence on inference for the slope, for example. And so just to demonstrate that relationship as well as a few others with a few different strategies for handling completely missing within study correlations, I have figures from results of a simulation study. So what I've done is I've used that two-level hierarchical model to simulate trial level summary data and then refit the meta regression for a variety of scenarios, depending on how the data was simulated. And so top left to bottom right, what I'm increasing is the average size of the within study correlation used to simulate the data. And then within any given plot, moving from left to right, the standard errors increase in size relative to the size of the between study standard deviations, defining how much variability there is between the treatment effects, the true treatment effects across your collection of trials. And then the different curves represent some of these different strategies that are used to handle the missing within study correlations very commonly in the surrogate literature. And so if you look at, for example, top left versus bottom right plots, this would indicate that the within study correlations are much stronger. But if you impute 0 or even use this uniform -1, prior, then the y-axis is bias in the meta regression slope through the posterior median in this case. And so there's a substantial amount more bias for an increasingly severe underestimation of the within study correlations. But this bias is minimized essentially close to 0 if actually the standard errors were 1/10 the size of the between study SDs. So you can do an evaluation to look at how much the average size of the standard errors relative to the between study SDs to determine the potential for which the missing correlations influence your inference. But if the standard errors are quite large, equivalent on average equal to the between study SDs, then the bias grows more severe. And so then one other piece of this analysis is that I've used this working on the terminology, this conservative prior. And so instead of assuming this uniform -1 prior says that on average the within study correlations are 0. But if you put a prior, so in this case I did a beta prior, which had the probability mass on the prior shifted up towards 1, and it won't be updated in the analysis because you apply it independently to each term. And so in this case, for a within study correlation of 0.8, this would be approximately getting it right in the sense that the prior probability emphasizes strong within study correlations. And so if you happen to do an analysis and utilize a conservative prior, then you minimize the potential for bias no matter the standard errors. Of course, you don't know this term, so this isn't something you'll be able to do in an applied analysis. So, but going to another plot, I think what this would essentially advocate for is a sensitivity analysis, looking at how much your posterior inference for the meta regression parameters changes as a result of prior specification. So things get a little bit better if we have partially missing within study correlations like the CKD Epi group does. And so we have two alternative strategies for handling missing within study correlations, which I'm terming a hierarchical beta prior and then conditional imputation of within study correlations. So for the hierarchical beta prior, what we do is we assign a common prior distribution to all the within study correlations. So this R hat sub J, like for the full spectrum of J representing trials, would include missing and non-missing within study correlations. So the within study correlations you have actually help inform or update posteriors for the priors you place on the missing terms. And so what we're finding can be helpful is that if you put, in some sense, conservative hyperpriors on this beta distribution. And so what these ultimately do is if I take draws from U and V in this way, so this beta distribution is again pushed for U, and sorry, U represents really the mean of this beta distribution. And this term, this prior is really shifted up towards 1 to emphasize strong correlations. And then that combined with this gamma 1,1 prior ultimately gives this beta distribution is again shifted towards 1. But the within study correlations will actually, again, update in the analysis through data fitting. And so if you ultimately have a large collection of smaller within study correlations, then the within study correlations that are in some sense imputed in the Bayesian model fitting for the missing terms are more likely to look like those available. But if you have mostly missing data, then this beta distribution will in some sense remain conservative again by overestimating within study correlations. And then another alternative approach that hasn't been discussed in the surrogate evaluation literature is that within study correlations are often closely related to trial level summary metrics that we actually have available. So in our case, the within study correlations are strongly related to baseline GFR in the trial's patient population. And so this is actually information that can be used to inform the missing within study correlations. And so what we're doing is transforming the missing within or all within study correlations so that they're continuous, and then modeling this transformed correlation conditional on a trial level summary metric. And so in our applied analysis, this would be like using baseline GFR. And then another simulation summary to represent sort of what we're seeing when we're utilizing these results to handle partially missing within study correlations. And so in this case, I've simulated data so that going down through the rows, these are results from utilizing these methods for handling missing within study correlations, where there's an increasingly large proportion of trials missing this term for the model fitting. And so, and in this case, the missing within study correlations come from a distribution that it's shifted up in the sense that the average missing term is a little bit stronger than the non-missing term or terms. And so what this indicates is that as the proportion missing grows, if the within study correlations you have available are not as strong as those that are not as strong as those that are non-missing, then you're increasingly going to have bias in the meta-regression parameter posterior. And then this coverage is the probability that the 95% posterior credible interval contains the true slope. And so this, as the posterior shifts up through the median, the whole posterior shifts up as well. And so what we're finding is that you can do a little bit better with these two alternative strategies, like applying the hierarchical beta prior or through this conditional imputation strategy, in the sense that even as the proportion of trials missing correlations increases, if you emphasize through the choice of your prior a higher missing within study correlation, then you're less likely to have this upward bias in the meta-regression slope. And then the conditional imputation appears to be imputing actually slightly stronger within study correlations than we're used to simulate the data. And so you actually have slight downward bias in the slope posteriors. And then just one more from this project. These are density curves for R squared for the meta-regression coefficient of determination, but now using the CKD Epi collection of clinical trials. And so I just have results for now for the case where we have complete missing within study correlations. And so for this, I used a collection of CKD Epi trials that have fully available within study correlations for all the trials. And so I'm plotting the posterior density curve with the dashed line from the analysis that we would have obtained if we use the within study correlations we have actually in our data. And then these other three curves represent R squared density curves that we would obtain from an analysis using these three completely missing within study correlations. And so the main point is just that it's not just the slope that's biased, and of course R squared is tied to the meta-regression slope as well as the residual variance. But if we hadn't collected individual patient data and we'd assumed that these terms were 0, or even in a Bayesian analysis assigned a uniform -1,1 prior, then these R squared density curves are really shifted substantially closer to 1, which would indicate as a result of the analysis that there's a much stronger relationship between surrogate clinical effects than we actually see in the data. And so some of the implications and recommendations from this project. Firstly and importantly, the specification of this missing term can strongly influence the analysis of the evaluation of a surrogate endpoint. And in particular, the underestimation of within study correlations can inflate the perceived strength of the quality of the surrogate endpoint. And this is quite important because you don't want to sort of validate a surrogate endpoint that ultimately would not be useful in a clinical trial for predicting clinically meaningful efficacy or harm, for example. And so the within study correlations can really only be ignored when the standard errors are very small relative to the between study variability and the treatment effects. And so if what we're finding is that if within study correlations are missing, you can potentially utilize what I've called a conservative prior, but ultimately it's advisable to collect within study individual patient data for at least some proportion of the trials. Whereas if you have some within study correlations, then you can consider this conditional imputation or this hierarchical beta prior strategies. So now I'll go over project number 2. Do you mind updating me on the time? Just so I know.
It's 12:38, so probably
10 more minutes?
10, 15 minutes, yeah.
Okay.
Time for questions.
Okay. We'll probably skip just a couple of the slides going through this part just for the sake of time. So for project 2, I've titled this Evaluation of Surrogate Endpoints where the quality of the surrogate may vary across subcategories of intervention mechanism or disease. And so especially for the CKD setting, in CKD, it's been written about that the use of clinical trials for evidence-based medicine has increased more slowly over time relative to many other specialties in medicine. And so to do this trial level evaluation of a surrogate endpoint, we're utilizing trials with a range of disease subcategories, all of which though have kidney relevant endpoints for patients with CKD. So we have diabetes trials or diabetic nephropathy trials, glomerular disease trials, and others. And because of this variety of diseases, we also have a variety of intervention classes that are being evaluated in this collection of trials, like SGLT2 inhibitors for the diabetes trials or immunosuppressants more often for the glomerular disease trials. And so the surrogate endpoints have been evaluated on this broad collection of trials, and regulatory agencies have expressed concern over the potential for the quality of the surrogate to vary across these subgroups of trials. And so most often in practice, a single model is fit to an overall collection of trials, ignoring the trial subgroup memberships. And so that would be like the model I introduced in the introduction section. It assumes full exchangeability of all the trials in some sense that there isn't some key mechanism that distinguishes one trial from another. And so this has been addressed in this space by fitting meta-regression models just completely independently within subgroups. But if you already start with a fairly small collection of trials, in our case 50 trials about right now, but if you further subdivide the trials, then you really lack information to fit a separate model within the subgroups. And this is especially the case because in some settings, the trials are often smaller. So even if you have 20 trials for one disease type, if they're very small trials, then the information content to fit a meta-regression model is very limited. And so, of course, this leads to excessive uncertainty in the parameter posteriors that obscures the true quality of the surrogate endpoint because of the estimation uncertainty. And then just a little bit more terminology for this section. So what the group has historically done is fit what I'll call a full pooling random effects model to the full collection of CKD Epi trials, ignoring the trial subgroup memberships. But then also the group has fit what I'll call now no pooling random effects models, fitting an independent model within the separate subgroups of trials. And so we're extending these two approaches by utilizing what I'll call a partial pooling random effects model, which allows for a subgroup specific meta-regression, but then we apply hierarchical structure in the model fitting to improve our estimation of subgroup specific parameters by inducing sort of a data adaptive information sharing across the subgroups. And so one thing that we're addressing in this paper is whether, so as I mentioned at the beginning, the CKD Epi group has historically assumed bivariate normality of the true treatment effects on the clinical and surrogate endpoints. But some other authors often just assume fixed effects for the true treatment effects on the surrogate endpoint, and then some have alternatively considered alternative distributional assumptions. But these distributional assumptions can influence the inference for the meta-regression parameter posteriors, because it really changes the amount of variability you have in the x-axis variable, in particular in the model fitting. And this is important to address in this question of evaluating or model fitting within subgroups, because of the fact that we want to make sure that if we're seeing different slopes across the subgroups, and this is because the surrogate actually varies in its quality and not because of a distributional assumption. And so we've also looked at what I'll call, for example, a partial pooling fixed effects model that assumes fixed true treatment effects on the surrogate endpoint in the analysis. So the model that we're proposing, the partial pooling random effects model, I have notation for that here, but I just want to emphasize a few key features to indicate what I mean by partial pooling. And so we assume the same first level model for the estimated treatment effects on the clinical and surrogate endpoint within each trial. But then there's an additional subscript I to indicate now that the trials are also embedded within subcategories defined possibly by disease or treatment class. And so we still assume a linear relationship between the true treatment effects on the clinical and surrogate endpoint, but we allow there to be a subgroup specific meta-regression slope, for example. And so we have that denoted because there's an extra subscript for beta. But then you can apply a between subgroup distribution for the meta-regression slope, as well as the other parameters, like a log. What we do is for a log transformed residual standard deviation. And so in the analysis, this means that we're estimating a between subgroup distribution, which partially pools the subgroup specific slopes. But it shares information across the subgroups so that we can actually estimate beta sub I with improved precision, although this can come at the cost of a little bit of bias in the analysis. So I have a conceptual demonstration here I might skip through for the sake of time. I'll just maybe highlight this here. So imagine that we're trying to estimate what I'm calling alpha 1 and alpha 2 by fitting a partial pooling model. And then in this case, two subgroups, and then we obtain the histograms meant to represent a posterior distribution obtained in the analysis. So what we expect to happen when we fit a partial pooling model is that the posterior distributions for the subgroup specific terms can be shifted slightly towards one of another because of the information sharing. But we have, should show this relevant to the previous slide. What we expect is that the information sharing improves the precision in the posteriors. And so you're able to distinguish that there's actually a difference between the two posteriors that we're actually obtaining from the analysis. This would be relative to a no pooling strategy, which has limited bias or little to no bias through the sort of the central tendency of a posterior distribution, but there's no information sharing. And so there's a lot of information lost in the analysis. And then these posteriors are wider, so that as a result of the inference, it's more difficult to evaluate whether or not the terms we're estimating are actually different. And so I'm just going to skip through to the results of some of our applied analyses on the actual CKD Epi data. And so what I'm highlighting here is again, a scatter plot containing trials, but for a particular CKD subgroup. In particular, these are, so we've grouped our trials into 3 disease-defined subgroups: diabetic kidney disease, glomerular disease, and then another subgroup would be CKD of unspecified cause, where there's actually an entire different class of interventions that are evaluated in this context. And so I have here prediction bands obtained from fitting the partial pooling random effects model, and then those from a no pooling model. So if I just fit the models independently within this subgroup, without utilizing information from the trials in the other subgroups. And so the key here is that the use of this partial pooling strategy just dramatically improves inference for the meta-regression posteriors relative to a no pooling model. And so if we were interested, for example, in predicting a treatment effect on a clinical endpoint from a treatment effect on the surrogate on the x-axis, then use of this model would really lead to such excessive imprecision in the posteriors that we get a completely unclear picture of the predicted clinical effect within this subgroup.
For the other, okay, the gray dots are the ones you're leaving out.
Yes,
Yeah.
all right, yeah. And then, so as I mentioned above, we're comparing these models that assume fixed two treatment effects on the surrogate endpoint. So in the analysis, you just apply an independent prior directly to each trial's true treatment effect on the clinical endpoint. And then this is for another disease-defined subgroup for the glomerular disease trials. And so when we fit the full pooling fixed effects model, this would be a regression line utilizing posterior medians from the meta-regression parameter posteriors. And the key is that the fixed effects models tend to underestimate the magnitude of the meta-regression slope relative to assigning the normal distributional assumption specifically to the true treatment effects on the surrogate endpoint. And this, in the simulation study, that it indicated actually that this was a downward bias in the partial pooling fixed effects models, specifically in subgroups with a stronger meta-regression slope. And so what we tended to find was that this, utilizing a fixed effects model, if you're doing a model-based prediction of clinical effects, you tended to underestimate the magnitude of the clinical effect corresponding to a given treatment effect on the surrogate endpoint when utilizing the partial pooling fixed effects models. So I know I skipped some of went over a little bit quickly, but some conclusions from these analyses. The proposed partial pooling random effects model strongly improved precision in the meta-regression parameter posteriors, overfitting separate models within subgroups of trials, and resulted in small bias in our simulation scenarios. The bias that's induced by this information sharing appears to have limited potential to impact the overall conclusions of the surrogate quality within subgroups. A fixed effects alternative to this partial pooling random effects model has been previously discussed, produce downward bias in the meta-regression slope in subgroups where the surrogate endpoint is strong. Again, it's specifically in those subgroups of trials where the surrogate is strong that the surrogate is most useful for predicting clinical effects. And so this partial pooling random effects model provided the highest coverage and posterior predictive precision in those subgroups of interest alternative to those considered. That's what I have for today.
Great, thank you. Questions?
I'm curious if any of this work has been what has been part of discussions with the FDA or with regulators about surrogates, or is this kind of completely separate theoretical work, or
Yeah.
if there's any overlap at all?
So the CKD Epi group is, I think they're working with the EMA on a specific proposal to evaluate look at how these surrogates are proposed. And so included in that documentation, we're looking at these subgroup analyses. Yeah.
And no conclusions out of that yet. I'm just curious how they responded to it.
In the applied analyses, like, yeah, so in the disease, they are interested in the disease-defined subgroups, and also there's this other phenomenon in the kidney disease trials that, and this goes a little bit beyond my understanding of the biology, but some of the therapies cause this short-term decline in GFR that doesn't represent like a long-term kidney damage.
Okay.
They call it an acute effect. So we also have acute effect defined subgroups, and just what we're finding fitting these partial pooling models is that there's little evidence for heterogeneity in the quality of the surrogate across the subgroups. In other words, for the disease-defined subgroups, if GFR slope measured over 3 years appears to be fairly high quality surrogate for the glomerular disease trials and the diabetic kidney disease trials. But the data is going to continue to be updated. And a lot of the diabetic kidney disease trials are looking at SGLT2 inhibitors, which are changing things a little bit, I think. They seem to be helping improve kidney function quite a bit.
Other questions?
Not right now. I was asked by, I've been asked by investigators for the last few months, but if it's disease-free soil and overall survival, that's surrogate in a fine blood, particularly for bladder cancer. So I wanted to go back and look at some of what they've been sending to see, because this looks like it could be readily applicable, particularly because you have different subgroups where the predicted value would be high, metastatic disease, pretty high correlation, non-metastatic disease, really not high correlation. And to see how it might do some of the bladder cancer studies we have here, because it seems to be a big issue. What is the right information? So I need to phone up so I can ask you difficult.
That's always exciting to look forward to. All right, any other questions?
Question. Question may be naive, because I really don't understand the context of this. So in your first part, you have a most basic graph that the truth has a slope, but if you have some surrogate, you may have a stronger slope.
Is it
Not
here?
this one.
The red and black dots.
Yeah.
Oh, yeah.
Yeah, I have a hard time understanding this because I know in some other part of statistics, there's a, for example, in measurement error.
Yeah.
When you have measurement error, you often have a attenuation. Attenuation means your estimate has a weaker coefficient instead of stronger. So what context would make surrogate giving you a stronger effect estimate?
Okay. Let's see. So I'm sorry, I'm just trying to tie it to this particular figure here. You mean in this sense, like, why is it that the red line even is steeper than the black line?
So I thought the gray line is the truth and the red line is the estimate.
Yeah.
Right. So what context would make that happen? Oftentimes having noise or having measurement error would make your estimate weaker or closer to zero. That's what's called attenuation.
Yeah. So I think I look at it as, in this analysis, we're ultimately just interested in the covariance between two endpoints, and then in the data, we observe there's two sources of covariance. There's between the true treatment effects and then additional covariance associated with the sampling error of the treatment effect estimates. And so the trial level covariance, like embedded in the black line, is covariability between trials. And then you get the additional strength in correlation if, for example, could be typically it's all of the trials have a positive within study correlation between the sampling errors. And I think the way that I think about it is that this within study correlation here that makes the red line steeper is closely tied to the correlation between the endpoints themselves. And so it's sort of like if there's noise in the positive direction for the surrogate, then there's also usually noise in the positive direction for the clinical endpoint. And so in the CKD Epi collection of trials, like, so as this plot indicates, so we're looking at a negative relationship. And so like and this is for GFR 3-year total slope, and the average within study correlation is -0.5. And so it's actually, there seems to be this strong negative correlation between the sampling errors, and there aren't any trials in the collection that have a positive correlation. So if you ignore that source of covariance, then that in the analysis, and it kind of gets embedded within the between study covariance. Right? I hope that makes sense.
You're forcing it to be zero in that red and black plot, right?
Yeah.
The
Oh, in this.
within study.
Yeah, well, in this case, I just,
The R hat J equals 0.
oh, in this case, maybe this plot is slightly misleading because I'm just fitting regression lines through simple linear regression, just like fitting an OLS model just for the sake of demonstration
But
here.
your red dots were sampled from a model where it's influenced by the fact that the set the RJ equals 0.
Yeah, I guess in this case, it effectively does assume that's what the red line would be. Haven't thought about it that way. Yeah.
All right, let's thank our speaker again. Yeah, I think there's
Thanks,
food
everyone.
outside on your way out, and thank you all for coming.
I'm gonna end the Zoom meeting.
What?
I'm gonna
Yeah,
end-
you can just say the.
Why when you
Yeah. Couple weeks, it'll be-